In today's video, we're going to look at the graphs of the 6 trig functions. So we're going to look at the graphs of sine x, cosine x, tan x, cosecant of x, secant of x, and cotangent of x. Okay, so we're going to look at what the graphs of all 6 of these look like. We're also going to look at some of their properties. So we're going to look at domain and range, x-intercept, y-intercept, maximums and minimums. And the other thing that I want to look at is the period and the amplitude of each of these graphs. That's the first thing that I want to define here, and then we're going to look at all of the graphs individually and look at each of those properties for the graphs. So first of all, what you'll notice about these trigonometric functions is that they are periodic. What does that mean? It means that if you take one part of that graph of the function and then repeat it over and over and over again, that will give you the graph of the whole function. Okay, so all of these trigonometric functions are periodic. If I take a certain part of the graph and repeat it over and over and over again, then I will end up with the whole graph of that function. Okay, so that's the first thing that we are going to define, is the periodic function. Okay, so that is the first thing that you will notice about all of these trigonometric functions. The part of that graph that you repeat over and over again to get the graph of the whole function is called a cycle. Next, I want to define the period and the amplitude for one of these graphs. So the period of the function is the length of that cycle. It's the length of that part of the graph that you can repeat over and over again to get the whole graph. So the period is just the length of the cycle. And the amplitude, again, for a periodic function, all of these relate to a periodic function. The amplitude of a periodic function is going to be the average of the largest and smallest values. So if I take the maximum and minimum values for a periodic function, add them together and divide by 2, so I'm taking the average of the maximum and the minimum value, that will give me the amplitude. Okay, so these are some extra things that we need to define in order to go ahead and look at all of the properties of these trigonometric functions and their graphs. We're going to start with y is equal to sine x. Okay, so we're looking at the graph of sine of x. This is what it looks like. It goes through the origin. Okay, so because it goes through the origin, that tells me that sine of 0 is 0. So when x is 0, then I get that value of y is 0. Don't confuse this with the x and y coordinates that we had from the unit circle. Okay, remember that whenever I'm looking at the angle, so in this case my angle is x, okay, but whenever I look at the angle, then sine of the angle will always give me the y coordinate on the unit circle. Cosine of the angle will give me the x coordinate on the unit circle. So please don't confuse the x and y's here. It's just convention in terms of what we name things. But what this tells me is that when I have an angle of 0, my y coordinate on the unit circle is going to be 0. That makes sense because when we've got an angle of 0, we are on that positive x-axis. Y is still 0. Okay, so that makes sense. That agrees with what we had before. I then have this point here. Okay, when I've got an angle of pi over 2 radians, then my y coordinate is going to be 1. Okay, again, this agrees with my unit circle. Sine of that angle of pi over 2 is sine of 90 degrees. It's the same thing. I'm on that positive y-axis. So on the unit circle, sine of the angle is my y coordinate, and my y coordinate at that point is 1. Okay, so all of these, you can pick each of these points and they correspond to exactly what we had from that unit circle. Okay. What I want to look at first is the domain. What x values can I plug in here? Just by convention, whenever we do these graphs of trigonometric functions, we tend to use radians. From here on out, you're going to see radians a lot more than you're going to see degrees. So I can plug in any value, any number of radians that I want, and get out a y value. I don't have any points here where if I plug in a particular angle, I'm going to get sine of that angle is undefined. Okay, it's defined everywhere, regardless of what angle I put in. So my domain is all real numbers. This graph carries on in both directions. We've only done it between negative 2 pi and 2 pi here. But because if you think about it, I can go around my unit circle in the positive and negative directions as many times as I like. Okay, it doesn't matter. I just end up with coterminal angles. So I can have 0, 4 pi, 6 pi, 8 pi. I can keep going. Okay, I can keep going around this circle. So my domain is all real numbers. What about the range? What is the range of my function? So what possible values can I get out of this, bearing in mind what I put in? Well, the largest value that I can get out is 1, okay? The largest sine value that I get whenever I put in any input is 1, okay? That's as high as this graph goes. The lowest value I get is negative 1, which tells me that my range is negative 1 to 1. My x-intercepts, now there's a lot of them, but they follow a pattern here. If we look here, my x-intercepts are at negative 2 pi, negative pi, 0, pi, 2 pi, etc. It's every multiple of pi. Okay, so if I ever plug in a multiple of pi radians into sine, I'm going to get out 0. Okay, which tells me that on my unit circle, at every single point where I have a multiple of pi, I'm going to get that my y coordinate is 0. That makes sense because at every multiple of pi, I'm on my x-axis, whether it be positive or negative x-axis, but I'm on the x-axis, which means that the y coordinate is 0, so the sine value for that angle is 0. So my x-intercepts are going to be every multiple of pi, and you can keep going again in both the positive and negative directions past negative 2 pi and 2 pi. So it keeps going because this particular function has a domain of all real numbers. The y-intercept, that's pretty easy to see. Okay, it's the origin, so the y-intercept is just at the point 0, 0. So when x is 0, y is 0. That's the only point it crosses the y-axis. How about the period of y is equal to sine x? Okay. Well, if we look at this graph, if I take this part here that I'm drawing in red, that is the part of the graph that I repeat over and over and over again in order to get the graph of the whole function. I have to take more, let me do this in yellow, I have to take more than just that yellow part there, because I'd have to deal with reflections, etc. if I just took one of those arches. I have to take one that goes above the x-axis and one that goes below the x-axis. That is a full cycle, because then all I do is I take a picture of that and I just repeat that over and over and over again to give me the graph of the whole y is equal to sine x function. So the red part is what I repeat over and over again. That is one cycle. What is the length of that cycle? It's 2 pi, okay? It's the distance along the x-axis that I have gone in order to get that cycle. So it's got length 2 pi. Same here. I've got another cycle that repeats here. That has length 2 pi. Okay, so the period of this function is 2 pi. What's its amplitude? Okay, the amplitude is the average of the highest and lowest numbers. Okay. Difficult to do here, because if you actually take the highest and lowest value and divide it by 2, when you add them together, you actually get 0, because 1 plus -1 is 0, divided by 2 is still 0. So what you actually do is you refer to this in terms of height. Okay, we're doing this in terms of height, which means we're looking at a length, so we only deal with positive numbers. This arch here has length 1, it has height 1. Okay, this arch here also has height 1. So what I'm going to do is I'm going to add together the heights of the two and then find their average. So I'm going to do 1 plus 1 over 2, which gives me 1. Okay, that will give me the average of the heights of this particular function. So I've taken the maximum, I've taken the minimum, but to find the average of the two, what I'm going to do is actually deal with them in terms of lengths, which means I make them both positive and then I divide by 2. How about the maximum and the minimum? Well, that's easy to see now that we've done that. The maximum value is 1 and the minimum value is -1. Okay, so now we are going to do the same for the graph of y is equal to cosine of x. You see it's very similar to that graph of sine of x. Okay, it still has this periodic wave function to it. Difference is that now we have some different x and y intercepts, but the majority of the rest of the properties remain the same, just to make sure that it agrees with what we had when we looked at the unit circle. If I plug in x is equal to 0, so my angle is 0. Think back to the unit circle. When I have an angle of 0, the cosine value of that angle is going to be 1. Because I am on that positive x-axis and I have a unit circle, my x-coordinate was 1. So when I had an angle of 0, my x-coordinate was 1, my y-coordinate was 0, which gives me a cosine value of 0 of 1. Sine of 0 is 0. Okay, so that's why we have this. Now, you can do the same with the rest of these points. If I plug in pi over 2 radians, okay, that's 90 degrees. Cosine of pi over 2 radians is 0, because the x-coordinate is 0 when we look at the angle of 90 degrees on our unit circle. So each of these is going to agree with what we had on that unit circle. Let's look at some of the properties. So first let's look at the domain. Same as with the sine function, I can carry on with this graph in both directions. Okay, I can plug in any x value and get out a y value here. I can plug in any angle into cosine and get an output. So my domain is still all real numbers. my range, well, the largest value that I get here is 1. The smallest value that I get is -1. So my range is -1 to 1. Then we need the x and y intercepts. Now this is different from our last graph. The x-intercepts, the way that we actually write this is as a set. Okay, what does this mean? What you'll see here is we have odd multiples of pi over 2, okay? Where we cross the x-axis is at pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, etc. And same in the negative direction. They are all odd multiples of pi over 2. So the way that we write that is pi over 2 plus multiples of pi. If I take pi over 2 and I add pi, I get 3 pi over 2. If I add another pi, I get 5 pi over 2, etc. So the way of writing odd multiples of pi over 2 is actually by writing it as this set. Pi over 2 plus integer multiples of pi, okay, where k is just that integer value. My y-intercept is at 0, 1. Okay, so I intercept the y-axis where y is equal to 1, and of course x is equal to 0 there because I am on the y-axis. Then, same as with my sine graph, the period and the amplitude are both the same. Okay. If I look at one cycle of this graph, you can take this cycle to be wherever you want. I can either have an arch and this arch and then repeat that over and over again as we have this wave. I could have also drawn this as repeating this cycle here. All of them have length 2 pi. So the period of this cycle is 2 pi. The length of the cycle is 2 pi. Amplitude exactly the same as we had with that sine graph. I take the lengths for the maximum and the minimum, find the average, and I get 1. The maximum and minimum are the same as before. So there's a couple differences here compared to that sine wave, but you'll find that this cosine graph is actually just a shifted version of the sine graph. Okay, I have moved it to the left by pi over 2. Okay, you can see that from where I drew my wave here. I'll do this in yellow. This was the exact same shape as my sine wave. I've just moved it to the left by pi over 2. Now we're going to look at the graph of y is equal to tan x. And like I have said previously with previous videos, tan does have asymptotes, okay? There are angles for which when I take tan of that angle, I get an undefined value out, okay? Y would be undefined. At that x value, I would get an asymptote. At that angle, I get an asymptote. Why is that? Well, you'll find, if we go back to our cosine graph here, remember, tan of x, or tan of theta, is equal to sine of the angle divided by cosine of the angle. If cosine of the angle equals 0, it means that I'm dividing by 0. So if we rewrite this as sine of x over cosine x, if there is some angle for which cosine of that angle equals 0, then I am taking sine of the angle divided by 0, which is obviously undefined. So if we look at where we get 0 out of our cosine graph, we see that cosine of pi over 2 is 0, okay, because I hit that x-axis. Cosine of pi over 2 is 0, cosine of 3 pi over 2 is 0, etc. Okay, it's all of those odd multiples of pi over 2, which is exactly what we see here with our asymptotes. At those odd multiples of pi over 2, where I got that the cosine of that angle was 0, I have an undefined value out of my tan function. And therefore, in the graph, I have asymptotes. So the graph is going to approach these vertical asymptotes, but it's never going to hit them because the graph is undefined at those values. We're going to do the same as we did with our sine and cosine graphs. We're going to look at some properties. So the first thing is the domain. What is the domain of our tan function? Well, there are some x values such that we have an undefined tan function. Okay, our tan function is undefined, and that is at all odd multiples of pi over 2. Okay, at every odd multiple of pi over 2, I get that tan of that angle doesn't exist. So my domain is all real numbers, and then we're going to take out all of those odd multiples of pi over 2, written exactly the same way as before. The range, this graph goes all the way up and up and up to infinity, and all the way down to negative infinity. So our range here is actually all real numbers. Tan can become a very, very large number. The reason being, if we divide whatever sine of an angle is, we divide that by cosine of the angle. The closer that cosine of an angle is to 0, I'm then dividing by a very small number, making the tan function incredibly large. Okay, so you will find that it will shoot off to infinity or negative infinity if we get a negative for sine or cosine. Then I need to look at the x-intercepts. Where do we cross the x-axis here? Well, we're crossing the x-axis at multiples of pi. So our x-intercepts are going to be all integer multiples of pi. The y-intercept, well, that's just the origin, as we can see here. Tan of 0 is 0, so our x-intercept, or our y-intercept is 0, 0. Then we need to look at the period of this. Okay. The cycle that we have here is just one of these curves. Okay. And the length of that is pi. You just repeat that cycle over and over again. So the length of that cycle is pi, so our period of this periodic function is pi. The amplitude. Well, here I actually have no maximum and minimum. Okay, so like before with sine and cosine, I had a maximum and minimum. But here, because I can go all the way to infinity and negative infinity, I don't have a maximum or minimum. Okay, you can't count infinity or negative infinity as a max or min. So my amplitude actually does not exist. There is no amplitude. Okay. Now we're going to look at the reciprocal functions. Okay, these graphs you don't see as often as the sine, cosine and tangent graphs, so they're the ones that you really need to know, but these ones will come up occasionally. So these are the reciprocal functions. So cosecant was the reciprocal of sine. So what I'm doing here, for each one of my angles, we've called them x in this case, I'm finding sine of the angle, and then I'm doing 1 divided by that output, and that would give me my y value. Okay. And this is going to be the graph that you get. So I do have some asymptotes here. Obviously, I will have an asymptote at any angle such that sine of that angle is 0, because I then get 1 divided by 0, which is undefined. So any angle that I have that makes sine of that angle 0 is going to give me an asymptote. Okay? So we see this here. At every multiple of pi, that was where the sine function crossed the x-axis, which means that the sine of every integer multiple of pi was 0, which means that the cosecant at those angles is going to be undefined because I get 1 divided by 0. So my domain here is all real numbers, but we're going to take out those integer multiples of pi. because that is where I get sine of x is equal to 0. For the range here, we actually have a very weird situation where we have -1 and below and +1 and above. So we actually have to write this in a very weird way as the union of two sets. We have between -∞ and -1, but we include -1, okay, because there are values where we do get that cosecant of the angle is -1. And then union with, we get 1 up to infinity. Again, we include 1 because we see here at pi/2 I get cosecant of pi/2 is 1. So 1 is included in my range. For our x and y intercepts for this graph, they actually don't exist. We don't have any x or y intercepts. The period. Okay. Remember, I need to take a full cycle such that if I were to take a picture of the cycle, all I would have to do is literally replace it over and over and over again, and that would give me the graph of the whole function. Now, this thing obviously goes off in both directions, but one cycle would be this and this, okay? Because if I were to take this picture, I would then just repeat that over and over and over again every 2 pi. So my period here is 2 pi. Remember to take both of those arches, okay? They are somewhat reflections of one another, but I have to take the full snapshot of the cycle so that that snapshot can just be copied over and over and over again, and that's what makes the graph. Now we have the amplitude again here, because I have no max and min because we go to infinity and -infinity, I again do not have an amplitude for this function. Next we're going to look at secant, okay? So remember, secant is 1 over cosine. I end up with a very similar situation to last time. If there are any angles x such that cosine of that angle is 0, then for secant I would get 1 divided by 0, so at that angle secant would be undefined. Okay? So at all of those values where that cosine graph crossed the x-axis, meaning that y was 0, so the output was 0, at all of those angles, I get that cosine is 0 and therefore secant is undefined. So that was at all odd multiples of pi/2. So that tells me that I therefore get asymptotes at those values. So my domain here is going to be all real numbers, but we're going to take out those odd multiples of pi/2. The range is the exact same as we had for cosecant, okay? I have to go from -infinity up to -1 and include -1. We can see that we get -1 at -pi, at pi, etc. And then I've got to also include the union of the set 1 up to infinity. Again, we include 1 because cosine of 0 is 1, so we do have some angles at which we do get 1 as an output. For our x-intercepts, they don't exist. There are no x-intercepts for this graph. And the y-intercept, there is one y-intercept, and it is at 0, 1. Period, exactly the same as before. Okay, I take 2 of these arches and that will give me 1 full cycle, and therefore I can see from my image here that that has a length of 2 pi. So the period is 2 pi. And I don't have any maximum or minimum or amplitude here, exactly the same as I had for cosecant, because I go to -infinity and infinity. If you want to, I highly encourage you just to kind of check these graphs against sine and cosine. So if you want to, just plug in a few angles into sine and cosine, then take the reciprocal of that result that you get and see where that falls on these graphs of these functions, just so that you can see for cosecant and secant kind of how these graphs lay out like this and where these points lie and how you get to these graphs, because I know they look kind of weird. So I would highly encourage you to do that with just a few points. The final graph that we have is cotangent of x. Okay, so again, cotangent is just 1 divided by the tangent of x, so 1 over tan x. And we end up with a similar situation to before, where there are values such that we get these asymptotes. Okay, so any value where I had tan of the angle equaled 0, I would get an asymptote at that particular angle, because I know I would therefore be doing 1 divided by 0 here, and that would not work. So at all of the values where tan of x equals 0, I now have asymptotes, which is at every multiple of pi. So that means that my domain here, this function is valid for all real numbers, but I've got to take out those multiples of pi, because at multiples of pi I get that tan of x equals 0, and therefore cotan of x would be undefined. Then I've got the range. Okay. My range here is just all real numbers. Okay, exactly the same as tan. It goes off to infinity and negative infinity and gets super close to those asymptotes. It just doesn't reach it. I will also point out on this graph, because it isn't that obvious, this axis is also an asymptote, so keep that in mind. The x-intercept, so where do we intercept the x-axis? That's at every odd multiple of pi over 2. Okay, it's negative 3 pi over 2, negative pi over 2, pi over 2, 3 pi over 2, 5 pi over 2, etc. So we have that same situation as before, where it's all odd multiples of pi over 2. And then the y-intercept does not exist, okay? There is no point where we cross the y-axis here. The period, well, let's look at one cycle of this graph. It would just be one of these curves here, and it has length pi, okay? I go from asymptote to asymptote here, so that would mean that I have a period of pi. And we don't have an amplitude here because our maximum and minimums don't exist. We go to infinity and negative infinity, so I don't have a maximum or minimum, and therefore don't have an amplitude. I highly recommend you go back through these graphs and take a look at them, and like I said, plug in a few of those angles just to see where those points lie on the graph, to see where these come from. But hopefully you can see from these properties kind of what happens with these functions a bit more, which will also help with that unit circle. We're going to look more at these graphs in the next video and actually look at things called phase shifts, and also transforming and translating the graphs of these functions.